Hello everybody, we are going to discuss chapter 16, chemistry of benzene. So far we have discussed what makes benzene aromatic, recall Huckel's rule, recall the structure of benzene where we have three conjugated double bonds, so double and single bonds, but we also spent a lot of time in understanding why the structure of benzene is completely uniform. So it is a hexagon. Each carbon is sp2 hybridized 120-degree bond angle, and each of those bond lengths is exactly the same. And the reason for that stems from, you got it, resonance. And then we spent a lot of time discussing the Huckel's rule for n plus 2 pi electron system, which makes benzene aromatic. But then if you recall, I also said that while the real deal is that we have, remember the circle? Yeah. So while the real deal is that the electrons are delocalized over all the 6 carbon atoms, in reality, when you are showing the mechanisms, I encourage you to draw one of the resonance structures. So just then localize that. We know that for all practical purposes the real deal is the circle, so that works well for nomenclature. But when we are talking about your reactivity, you have to make those electrons stationary to be able to understand the mechanism as to how the reaction takes place. All right, okay, let's get started. So first things first, benzene does not undergo electrophilic addition. Does that ring a bell from the last chapter when we talked about aromaticity? I want you to take a moment to pause me and just think about what your thoughts are. Why am I saying that benzene is something that does not undergo an addition reaction, but rather it undergoes electrophilic aromatic substitution? So pause me, take a minute, and we'll then discuss. If you wrote in your notes that benzene does not have a full double bond, you're absolutely on the right track. In order to undergo an addition reaction, recall this was the whole concept of benzene not being a 1,3,5 cyclohexatriene, right? So your electrons are not localized in between specific carbon atoms, and hence you can't have that addition reaction take place. It's not going to work as if you had 3 double bonds. On the other hand, it will actually go through a substitution reaction, and we are going to take a look at how that reaction takes place so that benzene gets to maintain its aromatic core. So even though the first couple steps might seem like, oh, that looks like an addition reaction, the end game is not the same, because benzene is aromatic, and having an aromatic core is kind of like being in the golden land. That's like having your really stable scenario, and benzene would not want to let go of that situation. Now when you think about benzene as a moiety on its own, would you consider that to be a Lewis acid or Lewis base? So take a moment, think about whether benzene, which contains 3 sets of alternating pi bonds, do you consider that to be a Lewis acid which seeks electrons, or would you rather consider that a Lewis base which could serve as a source of electron? If you consider that to be a Lewis base, you are absolutely on the right track, because benzene will react with an electrophile. And electrophiles are Lewis acids because they are seeking electrons. Benzene itself is going to serve as a Lewis base, and notice what is happening. One of the hydrogens is getting replaced by the electrophile. So overall in your reaction, there must be some step where there will be generation of an electrophile there must be another step where the aromatic ring would likely attack, and a third step where a rearomatization will take place. We are going to take a look at several reactions to give you an idea of how this works, but just so you know, we are not saying that your electrophile is going to get added on that double bond again. Benzene is not going to let go of its aromaticity. So in this chapter, we're going to consider five or six different type of reactions. Some are related to each other. So first things first, we are going to take a look at halogenation. That means how could you put halogen atoms such as chlorine, bromine, iodine. Typically, whenever we think about these, the size is such that bromination is the most well studied, followed by chlorination. Fluorination is typically too fast and iodination too slow because of the size, and so not much information might be known for that. But typically you would see that both chlorination and bromination, especially bromination, is really well studied. We will also spend time in going over nitration, where we are putting in a nitro group, an NO2, directly on the benzene ring. Now, if you think about it, at one point of time, when we discussed pharmaceuticals, I said that having nitrogen atoms in your pharmaceutical molecules is really a good thing, because that's how you would introduce polarity in the molecule. And so this is a great way to put that nitrogen directly on that benzene. So keep that in mind. Nitrogen is not connected to the benzene through something else. So this is a takeaway, that if you want to ever put in a nitrogen directly to the benzene ring, you have to go through a nitration step. It would be somewhere in the scheme of things. We will also talk about sulfonation, where we are putting in a sulfur atom directly on the benzene ring, and closely related to sulfonation is the hydroxylation. In fact, to go from one to another, you could actually convert a benzene sulfonic acid into phenol. You could totally do that. So sulfonation and hydroxylation are somewhat connected to each other. And then alkylation and acylation, we are going to talk about that through what is called as Friedel-Crafts. Those are the people. Alkylation, and then Friedel-Crafts acylation. One was a problem point, the other served as a solution, so we'll spend some time in discussing that as well. But either way, in all of them, one of the hydrogens on the benzene ring is going to get substituted by an incoming electrophile. So that's the reason we are calling it electrophilic aromatic substitution. Substitution because it's a substitution reaction, aromatic because it's happening on the benzene ring, and electrophilic because the incoming atom or group of atoms is electrophilic in nature, aka it has a positive charge, aka benzene is going to serve as a, you got it, nucleophile. All right, so as I said, whenever we run this reaction, benzene is going to utilize its pi electrons. It is a Lewis base, and your incoming electrophile is going to be the Lewis acid, because we know that Lewis acids are electron pair acceptors and Lewis bases are electron pair donors. So whenever these reactions take place, benzene is going to serve as our Lewis base. All right, let's see how the first one, which is halogenation of benzene, take place. All right, so as we discussed, benzene is going to serve as the Lewis base. That will be your nucleophile, and it's going to seek an electrophile, and the reaction will take place, and your product, bromobenzene, will be generated. Your overall reaction is shown very nicely over here, where we have shown you benzene and it's reacting with bromine in presence of FeBr3. That is your catalyst, your Lewis acid catalyst, which is going to polarize your bromine, and the final reaction will take place, and bromobenzene is born. Now, one easy way to identify what that electrophile would be to just look at, just compare, because if you recall your generic reaction, I gave you that if you have benzene, right, I showed that as an H, and then we said that there could be an electrophile, so let's call that E plus. And the final product was that we are going to end up getting the substitution, and the H plus would be allowed to leave. So if I compare my generic reaction that I showed you to this bromination, what do you think this E plus would be? It's the E that ends up being on the benzene ring. So what do you think should be E plus? Absolutely, bromine plus. So whatever is the atom or group of atoms that might be present on your aromatic nucleus, take that, and of course that must have a positive charge to identify your electrophile. Okay, so this is an unsaid thing that you must keep a track of, that whenever you are carrying out an electrophilic aromatic substitution reaction, you have to identify the electrophile. Just look at the product, and this is of course if you are given the reaction and then a mechanism is asked. If you're supposed to predict, you're supposed to know what how the whole 9 yards works. But just to get started, this is a good strategy to have, that whatever is the atom or the group of atoms that is connected right on the benzene ring, that with a positive charge would be your electrophile, because electrophiles are supposed to seek electrons. Everybody good? Good. So we are going to now take our bromine and recall something about bromine from your organic 1 days, that bromine is polarizable, right? So because of the size of bromine, it can generate a delta plus and a delta minus, so that bond can polarize. It's not like a radical type reaction, right? So that polarizable bromine-bromine bond, when reacted with FeBr3, what happens? Essentially, iron starts to coordinate, because it's a D block element, it starts to coordinate with the negative end of your bromine-bromine bond, and it's going to form this polarization. It's going to occur more strongly. All right. What this means is that now you can break this bromine-bromine bond even more easily than before. Now this has the capability, if this bromine-bromine bond breaks, this has the capability to form Br plus and FeBr4 with a negative charge. Now that's a complex ion, and so one of the bromines we are saying is going to stay coordinated with the D or among the d orbitals of the FeBr3. So we have just generated our electrophile. So that first step that we were discussing, that we have to generate an electrophile, we just did that. And how did we do that? Again, we are starting with a bromine-bromine bond, which is a polarizable molecule, that upon treatment, it does require the presence of that Lewis acid catalyst, which is going to cause a stronger polarization of the bromine-bromine bond. And when that happens, it's going to cause the formation of a much stronger Lewis acid, which is then going to be attacked by your benzene ring for furthering the reaction. So the next step would be maybe we can just show that coordination. This is delta minus, this is delta plus, and we saw previously that it's going to be FeBr3, which is going to coordinate with the negative N to first form this complex. Notice this bond is ready to break. And it will break, right? So as the attack takes place, this is going to go away, generating the Br plus, which is where the benzene is going to attack. So your end product is going to look like let's erase that a bit. And it's up to you which bond you really want to utilize for showing your reaction. I just chose let's just number them for the sake of numbering. It's important to recognize that each of these positions do have a hydrogen, and the atom which has given the electron, so you have to visualize that you had 2 electrons here, and now both of those electrons are being used in forming the bond with bromine. So if you think about who's the ultimate loser in terms of losing those electrons, that would be position 1, right? This is your intermediate. Do you think this is aromatic? Absolutely not. And so what should happen? Is this intermediate happy? It does have resonance, of course, but it has just lost its aromaticity. So it's not like in the La La Land, right? So it wants to get rid of this scenario because it's slightly higher in energy. So that Br minus is going to come in. It's going to pick up the proton. Electrons are going to go back on the benzene nucleus. Bromine is still connected where it's supposed to be. HBr is your side product. And of course the FeBr3, that was the catalyst, so it had to get regenerated again, right? So that's how you get the formation of bromobenzene from benzene. So this question was draw the mechanism of bromination of benzene and note the formation of carbocation, which is your intermediate, which we just did. So this is your intermediate. Intermediates, no matter how stable they are going to be always higher in energy as compared to your starting reactant, because those are typically charged species, and so they will have some sense of reactivity for reacting with any electron source if that is available. All right, let's take a look at another one. The question here says, draw and name the 3 possible products of the bromination of toluene, not including HBr. So they're saying that HBr is a product you're going to see in any of these reactions, but what are the possibilities if you started with toluene? Anybody remember what is the structure of toluene? So you have benzene, of course, a methyl group, right? So methyl group on a benzene ring is toluene. And we are going to react it with the same reaction condition, Br2, FeBr3. Of course, it's going to go through the mechanism. Notice they haven't asked for the mechanism, so I'm not going to spend the time in writing one. This is one of those cases where you could be given, in your first test, for example, I like to call these box problems, but really it's a fill-in-the-blank problem. where you are being asked to convert. So you're given your starting reagents, you're given your reaction conditions, and then the products need to be written down, right? That's what they are asking. Another way to view this would be if it was a prepare question. So how would you prepare bromobenzene from benzene, right? Or in this case, you're starting with toluene. So starting with toluene or convert toluene. So two words to kind of keep in mind. Prepare, and that means they will say the product first from whatever is your starting material. And when they use the word convert, that means they will say convert starting material into, and then they will say the name of the product. But either way, this reaction sequence is going to allow you, it's going to help you with the design process as to what should you do when. Not in this video, but pretty soon we are going to talk about what are called as substituent effects. And so then we would be able to kind of dig deeper as to how do we strategize, what comes first, what should be the first reaction, what will work, what will not. But at this point of time, for the purpose of this question, let's focus on what we have been given. We have been given a methyl group. So obviously we are not going to touch that. Hopefully everybody can see that in this case, this Br2 FeBr3, that reaction condition is for the aromatic ring. Right? So it's not going to touch the CH3 over here. It's not going to touch the ipso position over there. The only places that can undergo substitution process are going to be the ortho positions, the meta positions, and the para position. And notice that the ortho positions are exactly the same, the meta positions are exactly the same, and the para is by itself. So what should go as the product? Yeah, you just draw them out. Of course, the benzene ring is going to stay like that. The methyl group is not going to go anywhere. That's not going to undergo substitution. It's the hydrogens that undergo substitution. So feel free to put down the bromine on either of the ortho positions, either side. If left is your favorite side, put it on the left or right, as the case may be. Both of those are identical positions. Likewise, if you want to put a meta, that's how you would show that. And if you wanted to show a para, that's how you are going to show that. So those are your three possibilities. And again, they did not want us to count the HBr, so I'm not going to do that. All right. Okay, let's take a close look at chlorination. This is something very similar to bromination. That means you are going to generate, we called that bromonium ion earlier. Br plus was bromonium ion. So Cl plus will be chloronium ion. Note that it's not necessary that if I just have Cl2, then I must always just use FeCl3. I could, if I wanted to use FeBr3, if that's what I had in the lab. The reaction will still work the same way, but just for consistency purposes, they kind of use the chloride as the conjugate base for when it's a chlorination, the bromide as the conjugate base for when it's bromination. But you could, if you wanted to, mix Cl2 with FeBr3, the reaction is still going to work, because know that the activation is going to affect the Cl-Cl bond with the Fe. This part of the molecule doesn't quite participate in the reaction, okay? So keep that idea in mind, that when the reaction takes place, it is the Cl-Cl bond which is going to interact with your FeCl3 or FeBr3, whichever you're picking up. The end product is that you would be able to put in the chlorine directly on the benzene ring. That means you would have substituted one of the hydrogens with the Cl atom. Okay, let's talk about iodination. Much like bromination and chlorination, but iodine is fairly unreactive towards aromatic rings. And part of it has got to do with the idea since this reaction for iodination is a fairly endothermic reaction, 12 kilocalories per mole will be required for the reaction. So it's very endothermic in nature. And for that reason, it has to be given a little bit of a nudge. And typically, that is done by using oxidizing agents such as CuCl2 or H2O2. Sometimes iodic acid might be used as well to make the iodine a little bit more reactive and generate a usable form of iodine. Okay, so let's take a look how the reaction takes place. However, I should say that since iodination is poorly understood, these are not the complete steps for the iodination. This is just more of a model, but this is not a complete reaction how it takes place. I will try to explain some of the steps as we go to show you the comparison as to what other possibilities are there. But it should be considered that this is a fairly poorly studied reaction and typically not done actually in the real scenario. Most people would go with bromination or chlorination, not with iodination, unless that is the requirement. Simplistically saying, one could say that iodine is reacting with the Lewis acid catalyst here, which is also the oxidant. It's going to oxidize the I2 to I plus. That means I2 is going from I0 to a +1 state, hence oxidation. And Cu2 plus, which is a peacock blue color, is going to reduce into a brick red color, which will be just one single plus sign. So hence that reaction is the reduction reaction. Of course, as the reaction takes place, it does go through a coordination with the COCl2, in which case now when the I bonded to the COCl2 leaves, it leaves behind the I plus. At a later time, the ICuCl2 would allow the loss of CuCl2. And when you generate that compound back again, it's going to go through a second sequence of reaction. Essentially, when this reaction goes through, a lot of times a base may be added for forcing the reaction to go, a base like NaHCO3, for example, to absorb the HI that gets generated as a final step. So again, as a first step, your benzene is going to attack the iodine as the I plus. That will generate the resonance stabilized, but know that this is not an aromatic intermediate. And as the last step, the I minus that had gotten generated, that was floating around in the reaction, is going to pick up your H that generates your iodobenzene. There are some other methods that have been put forth. For example, the use of ICl versus I2. Because ICl is a somewhat polar bond already, right? It has a greater tendency to generate your I plus species. There is evidence that ICl used with a Lewis acid catalyst like AlCl3 would readily generate the I plus ion. So this is iodine monochloride, and it will go through the reaction. Just in the last step, your base that is going to pick up the proton would be Cl minus, right? So there are other versions of the reaction that people have tried, but all in all, because iodination is kind of a difficult reaction to go through, being extremely endothermic, it doesn't find a lot of traction in practical organic chemistry. So unless people had to form that iodobenzene, there was no other solution to that, they would not typically go for this particular halogenation.